Alright, so good morning. We're going over 3.5, which is factoring complex zeros and rational root theorems. We're going to start with factoring a polynomial completely. So we're going to let p of x equal negative x, or x cubed minus 3x squared plus x minus 3. We want to find first all of the zeros of p, and then find the completely factorization of p. So how am I going to do it? I'm going to grab the equation we have, which is the x cubed minus the 3x squared plus x minus 3. It's already in standard form, so I'm not going to rewrite it. I'm going to go ahead and do grouping. I can take out an x squared over here. I'm left with x minus 3. And I can take out a 1 on the other one, so I'm left with x minus 3. I write the new parentheses, which is x squared plus 1, and then x minus 3. We're almost done factoring. We're going to equal it to 0. Each parenthesis, so it's going to be x squared plus 1 equal to 0. And then x minus 3 is equal to 0. I add the 3 and I get x is equal to 3. If I subtract the 1, I get x squared is equal to negative 1. I'll take the square root, and I'm left with x is equal to plus or minus I, because we have a negative 1. Now your zeros are going to be 3, I, and negative I. If you write them as x is equal to 3, comma, plus or minus I, or if you write them x is equal to 3, x is equal to I, and x is equal to negative I, those are all valid answers for part A. Now for part B, they want us to write them into the factorization form, which just means that you're going to grab these three terms and put them all equal to 0. So you're going to be left with x minus 3, x minus I, and then x plus I. So your final answer for the factorization form is going to be x minus 3, x minus I, and x plus I. So this is going to be your answer for B. And this is going to be your answer for A. So zeros and their multiplicities. So in the complete factorization theorem, the numbers C1, C2, and all the way to Cn are the zeros of P. Now these zeros need not all be different in the factors of x minus c. Appears k times in the complete factorization of P of x. Then we say that c is a zero of multiplicity k. So for example, what does that mean? That means that you can have a lot of different zeros, but it could be the same number multiple times. So if we have p of x equals x minus 1 cubed, x plus 2 squared, and x plus 3 cubed, that means if I were to solve for these, which is x minus 1 equal to 0, we get x is equal to 1. This one's equal to 0, so we get x is equal to negative 2. And here we have x plus 3 is equal to 0, and we get x is equal to negative 3. That means this one has a multiplicity of 3, this negative 2 has a multiplicity of 2, and this negative 3 has a multiplicity of 5. That just means, do you remember what we talked about when it bounces off of the x-axis or it goes through the x-axis last semester? That's what this multiplicity does if you were to graph it. One bounces off and one goes right over it through, depending if it's odd or even. Now, if we have a multiplicity of 3, you would write, well, x is equal to 1. We're going to make it into a parenthesis, so x minus 1 is equal to 0. So we get x minus 1 with a multiplicity of 3, so we're going to cube it. We have x is equal to negative 2. We're going to make it into a parenthesis, so it's going to be x plus 2, multiplicity of 2, so we're going to put it as a square, which is exactly what we have. We're just working backwards, and we have x is equal to negative 3. So x plus 3 is equal to 0. That means we have that multiplicity of 5. So we know how to work one way and the other, and how it looks if you guys have different multiplicities. Now zeros and their multiplicities. The polynomial p has the same number of zeros as its degrees. It has degree 10 and has 10 zeros, provided that we count multiplicities. This is true for all polynomials, as we proved in the following theorem. Zeros theorems, every polynomial of degree n is greater than or equal to 1 and has exactly n zeros, provided that a zero of multiplicity k is counted k times. Again, this is just talking about how many zeros repeat. So if you have a degree of 5 for a polynomial, you're going to get 5 zeros, but that doesn't mean you're going to get 5 x's. You can get a zero that is multiple, so you can get 3 answers, but one of them has a multiplicity of 2, or you can have 2 answers, one a multiplicity of 2, one a multiplicity of 3. All of those are possible. It just depends on the zeros. So zeros and their multiplicity. The following table gives further explanation of the polynomials with their complete factorizations and zeros. So if we have a degree 1, that means that our x has a exponent of 1 or not written. It's going to have 1, 0. So if it has a degree of 1, it's going to have 1, 0. If it has a degree of 2, it's going to have 2 zeros. A degree of 3, 3 zeros. Degree of 4, 4 zeros. Degree of 5, 5 zeros. Now, if you guys keep notice, for example, for the degree of 2, they factored it, or the equation got factored right here. So because it got factored, you notice we get x minus 5 twice, so we have 5 in a multiplicity of 2. Yes, we only have one number that is 0, but because it has a multiplicity of 2, we have 2 solutions. So sometimes you will have different solutions. Like number 3, we have I and negative I. Technically, i's are not real solutions because they're imaginary numbers, but they do count as zeros. So degree of 3, 3 zeros. 4, 4 zeros. Whether one of them is imaginary or not, as we see right here, both of the answers are imaginary. And then for 5, they're not imaginary, but they have different multiplicities. 0 having a multiplicity of 3, and 1 having a multiplicity of 2. Those add up to give us 5 zeros. So just something to check your work with when you're solving these. Since we're working with imaginary numbers, look for the degree of the equation, and that's the amount of zeros you need to have. Whether it's imaginary or not, you have to count them in order to match those numbers. If you have the same amount, you know you probably did it correctly. Now finding polynomials with specified zeros. So find the polynomial p of x of degree of 4 with zeros I, negative I, 2, and 2, and with p of 3 equal to 25. Now, you don't need this, the p of 3 equal to 25. We're just going to find the polynomial. Once you find the polynomial, you can check it by plugging in the 3, but it's not necessary. So I'm going to go ahead and do A. So it's going to be my first x is equal to I, my second x is equal to negative I, my third x is equal to 2, and my fourth is equal to negative 2. Now they're telling us it's a degree of 4. We have 4 zeros. We can just go ahead and write these in. So this is going to become x minus I. This is going to become x plus I. This one's going to become x minus 2. And this one's going to become x plus 2. Now for us to solve it, I'm just going to go ahead and write them. X minus I, x plus I, x minus 2, x plus 2. I'm going to go ahead and FOIL them to get the most simplified version. So this is going to give me x squared plus xi plus minus I minus I squared. And then this is going to be x squared minus 4. This is going to simplify to x squared. Remember, this is minus negative 1. So this is going to become positive 1. So plus 1. And then x squared minus 4. I can keep simplifying. I'm going to go up here. And I'm going to get x to the 4th minus 4x squared plus x squared minus 4. So we're going to get x to the 4th minus 3x squared minus 4. Here you already solved the polynomial, and that would be your solution. P of x equals the x to the 4th minus 3x squared minus 4. All right, so now let's look at B. They want us to find the zeros of the polynomial q of x of degree of 4. So again, we need 4 zeros. We have x is equal to -2. And we have x is equal to 0, where -2 is a multiplicity of 3. Alright, knowing that, I'm going to write this parentheses 3 times. So this parentheses is going to be x plus 2. That's a multiplicity of 3. And this is just going to be x, because x plus 0 is just x. So I'm going to write q of x equals x, and then x plus 2. Now I'm going to write it out expanded already, because x plus 2, even if I don't write it expanded, I need to FOIL it 3 times. So I'm just going to write it out. So this is going to become x squared plus 2x. And then this one on the right is going to become x squared plus 2x plus 2x plus 4. So this is going to become x squared plus 2x. And the right one's going to simplify to x squared plus 4x plus 4. I'm going to go ahead and FOIL the x squared plus 2x with the x squared plus 4x plus 4. This is going to give me x to the 4th plus 4x cubed plus 4x squared plus 2x to the 4th, to the 3rd, 8x squared, and 8x. Now I'm going to go ahead and simplify them. I only have one x to the 4th, so I'm going to write x to the 4th. So q of x equals x to the 4th. Then I'm going to write cube. I have the 4x cubed and the 2x cubed. That's going to be plus 6x cubed. I have to square the 4x squared and the 8x squared. That's going to be 12x squared. And then I have the 8x left over, so I'm just going to rewrite it. And then this would be your final answer. So we have complex zeros come in conjugate pairs. As you might have noticed from the example so far, the complex zeros of polynomials with real coefficients comes in pairs. Whether it's a plus bi is a 0 or its complete conjugate a minus bi. We saw this with, I think, last example, a that we have x plus 2x minus 2. That's a conjugate of each other. It's when you have the exact same parentheses but different signs in the middle. That's the whole difference. We have a plus and a minus, but it's the exact same parentheses. Now, conjugate zeros theorems. If the polynomial p has a real coefficient and its complex number z is a 0 of p, then its complex conjugate z is also a 0 of p. That just means that if we have the opposite signs for the equation as we have x plus 2x minus 2, that means that you're going to have the 0 being a positive value and the 0 being a negative value, which in problem A from the last slide, it was a positive 2 and a negative 2. So example 6 is a polynomial with a specified complex 0. So find a polynomial p of x of degree of 3. So we're looking for 3 parentheses at the very minimum or maximum. We should have 3 parentheses. That has an integer coefficient of 0.5 and 3 minus I. Now, since we're talking about the conjugate theorem, this 3 minus I, we can say, well, x is equal to 3 minus I, and x is equal to 3 plus I. Now, we were doing it with imaginary numbers in the last slide, which is the theorem. This is why we can go ahead and do this. We're going to move this whole thing to the other side, so we're going to get x minus 3 minus I is equal to 0. I can distribute that x to get the negative x minus 3 plus I. Then I'm going to do the same thing on the other side, so I'm going to be left with x minus 3 minus I for the other one. In this one, I did it in one step. In this one, I showed you the steps for both. Here we have one parenthesis. Here we have another parenthesis. And then the third parenthesis is going to be our x equals 2.5. Now remember, for fractions, you want to You can either move the whole fraction. You have two options. You have the first option, which is just moving the whole fraction like this, and then dealing with the fraction. The second option is when you equal this to 0, or not equal it to 0. When you want to make this equation equal to 0, you can multiply by the denominator first to cancel out that bottom, and you get 2x is equal to 1. Then you subtract the 1 and get 2x minus 1 is equal to 0. And you get that parentheses. Or you can do the x minus half. These two parentheses are the exact same thing. It's just one of them has a fraction and one of them doesn't. It's up to you which one you choose. You will get the same solution. Now, since I'm going to show you both ways, I'm going to start with the fractions, which is the easiest, as you just move the fraction over. So I'm going to start with the x minus a half, and we have the x minus 3 plus I, x minus 3 minus I. Now I'm going to go ahead and distribute the i's first to get rid of the imaginary numbers. This is going to be x squared minus 3x minus ix. And then it's going to be minus 3x plus 9 plus 3i. And then it's going to be plus xi minus 3i plus I squared. Now I'm going to go ahead and simplify that. Now we get x squared. Let me see what else I can get rid of. I have a negative ix, positive ix. Are there any other i's? Positive 3i, negative 3i. Okay, I'm going to combine what I can. So x squared, negative 3x is going to give me negative 6x. And then I have plus 9, and then plus negative 1, because the I squared. So this is going to simplify to x minus a half, x squared minus 6x plus 10. Because it's squared, it becomes positive. Now I'm going to start to deal with the fractions. So we're going to FOIL, and I'm going to get x cubed minus 6x squared plus 10x minus a half x squared plus 3x minus 5. I went ahead and when I distribute the fraction, I just simplified it right off the bat. So this is going to become x cubed minus 6x squared minus a half x. I'll combine the fractions in a second. Then this is going to become 13x minus 5. Now when I do 6 over 1 and a half, this is going to become 12. They're both negative, so it's going to be 13 over 2. So we're going to get x squared minus 13 over 2, x squared plus 13x minus 5. This is using the fractions x minus a half. You can also do it with the 2x minus 1 and not deal with the fractions at the end. But the fractions don't really get in the way until the very end of these type of problems. So it's not a big deal if you leave them to the last parentheses. Now I'll also show you how to do it with the 2x minus 1. If you guys are okay with it, I'll go ahead and erase this parentheses. Okay. Now I'm not going to erase the other stuff on the right just because we are going to FOIL that anyway. So this is now 2x minus 1, 2x minus 1, 2x minus 1, 2x minus 1. Now you can FOIL the 2x minus 1. You're going to get 2x cubed. Okay, let me erase the bottom. I'm going to run out of space. Again, either one of these, they're not going to be exactly the same because you're multiplying different numbers. But if you were to plug something in, it's going to give you the same solution. So it's going to become 2x cubed minus 12x squared plus 20x. And then minus x squared plus 6x minus 10. And I can go ahead and write 2x cubed minus 14x squared plus 26x minus 10. This is also a solution. Again, I know they're different, but you will get the same thing if you plug in a number. We have seen that a polynomial factors completely into linear factors if we use complex numbers. If we don't use complex numbers, then a polynomial with a real coefficient can always be factored into linear and quadratic factors. We use this property when we study partial fractions. A quadratic polynomial with no real zero is called irreducible over the real numbers, such as polynomials cannot be factored without using any complex numbers. So that's what we usually write in when it's for a prime factor that you can't keep going. When you write prime or not soluble, technically the word, the definition word is that one. But if you keep writing prime or not possible, that's still fine. It's just now you actually have a word that you didn't before. So linear and quadratic factors theorem. So every polynomial with a real coefficient can be factored into a product of linear and irreducible quadratic factors with real coefficients. What does that mean? We're going to go into the example to show you guys. So we have p of x equals x to the fourth plus 2x squared minus 8. And it says for a, factor p into a linear and irreducible quadratic factors with real coefficients. So for a, I'm going to go ahead and rewrite it. So we have x to the fourth plus 2x squared minus 8. I'm going to look for factors of negative 8 that add up to positive 2. So we have factors of negative 8 are 1 and 8. 2 and 4, I can do positive 4 and negative 2. This will add up to positive 2 and multiply to negative 8. Now, because it's the 4, you can break it up into an x squared. I'm going to say minus 2. And an x squared, which is plus 4. Now, this will be your solution for part A. They're just saying to write them into a linear, irreducible, quadratic factors with real coefficients. So that will be your answer for A. Now for B, they want us to factor P completely into linear factors with complex coefficients. So they want you to take this a step further by, sorry, I forgot to write P of x, by actually solving this equation and finding the zeros. So A is just the factors that are obviously real in this case, and B are the zeros, in other words. So you're going to get P of x is equal to x squared minus 2, x squared plus 4. We're going to equal that to 0. So P of x is going to become 0. So we're going to get x squared minus 2 is equal to 0. And x squared plus 4 is equal to 0. I'm going to go ahead and add the 2. So I get x squared is equal to 2. Take the square root and we get x is equal to plus or minus root 2. Here we're going to subtract by 4. And we get x squared is equal to negative 4. I'll take the square root, and that's going to become x is equal to plus or minus 2i. So your solutions are the positive and the negative root of 2, and the positive and negative 2i. So again, P would just be including the complex coefficients, meaning the imaginary numbers, and A would be just to write the factored equation, the linear equation in factor form, but not solving it yet. So in other words, just factors. So they want us to write the polynomial giving the roots. So we have 2 and negative 5i. So remember, this is a conjugate because we have an I. So we're going to get x is equal to 2, x is equal to negative 5i, and x is also equal to positive 5i. So that means we're going to have x minus 2, x plus 5i, and then x minus 5i. So my solution, I'm going to just write P of x. That's what we've been using for the whole note, so I'm just going to keep it. We're going to have x minus 2, x plus 5i, and x minus 5i. The reason we use the conjugate for the roots is because when we multiply them, they will disappear, and you will have the original equation with no i's, which is exactly what we're looking for in order for us to write the equation with all real numbers. Now, this will be the answer. Now, for 5, they want us to do the same thing. Again, remember, this is a conjugate because we wanted to not have any imaginary numbers in the original equation. If you were to FOIL this, for now, they're just asking for the polynomial given the roots. So we have x is equal to -7, x is equal to 2 plus 3i, and x is equal to 2 minus 3i. So we're going to get x plus 7 for one parentheses. Here we're going to get x minus 2 minus 3i. And here we're going to get x minus 2 plus 3i. So we're going to get a p of x plus 7, x minus 2 minus 3i, and then x minus 2 plus 3i. Again, don't worry about if it's p of x, f of x, h of x. Any letter of x or any other number is fine, or letter is fine. I'm just using p of x because that's what we've been using for the whole time for the notes. But again, you could use f of x if you feel more comfortable. Now we have 6. We have x is equal to 6. And we have x is equal to -5 minus 2i. Again, this is a conjugate because we want to get rid of the I. So I'm going to rewrite it as well into x is equal to -5 plus 2i. Now we're going to get a parentheses of x minus 6. And here we're going to have a parentheses of x plus 5 plus 2i. And we're going to have another parentheses of x plus 5 minus 2i. So we're going to be with the solution of p of x is equal to x minus 6, x plus 5 plus 2i, and x plus 5 minus 2i. Alright, so for 7, use the given zeros to find all the zeros of the function. So we know we have f of x equals x cubed minus 11x squared plus 43x minus 65, and they're telling us a 0 is 3 plus 2i. The only way for us to be able to solve this, because it's an imaginary number, is to first find what the zeros are, like the real number would be. So I have the x is equal to 3 plus 2i and 3 minus 2i, so this is going to become x minus 3 minus 2i. And this is going to become x minus 3 plus 2i. I'm going to go ahead and FOIL them. So we're going to get x squared minus 3x plus 2ix minus 3x plus 9 minus 6i minus 2ix plus 6i minus 4i squared. So I'm going to be left with x squared for the first one. I'm going to look at all the x's. We have 2ix and minus 2ix. We have plus 6i and minus 6i. So I'm going to go ahead and combine the other one. So I have negative 3x. That's going to be minus 6x. Then I have plus 9, and then minus 4 times negative 1. It's going to become plus 4, so we're left with x squared minus 6x plus 9 plus 4, which is going to give me x squared minus 6x plus 13. Now, why did I get that first? Because I can do long division with the equations. I can divide this one divided by the 0. You can also use synthetic, but I feel like factors of 13 are not fun, and you already got the 0. So it just might be easier to do a long division. So it's going to be x cubed minus 11x squared plus 43x minus 65 I'm going to go ahead and write it out for long division. So I'm going to start with x. So it's going to be x cubed minus 6x squared plus 13x. Now remember, when we're subtracting, we subtract everything. So this becomes negative, this becomes positive, and this one becomes negative. The x cubes cancel out. This is going to become negative 5x squared. This is going to become plus 30x, and I can bring down the 65. So negative 65. Now the second thing I want to do is I'm going to multiply by negative 5. So it's going to become negative 5x squared positive 30x minus 65. Again, remember, when we are subtracting, we subtract the whole thing, so we distribute that negative. This becomes positive, this one becomes negative, and this one becomes positive. So when I go ahead and add them, this one cancels, second one cancels, and the third cancels. So we have the equation x minus 5 is equal to 0. This is another 0. We have the original 0, which is 3 plus 2i, and its conjugate, which is 3 minus 2i. So your solution would be these three. All right, for 8, same instruction. We have this function g of x equals x cubed plus 11x squared plus 57x plus 203. And it tells us we have a 0 of negative 2 minus 5i. Again, I want to get rid of the imaginary number so I can do long division in order to get the other 0, or the other zeros, plural. So I'm going to go ahead and write x is equal to negative 2 minus 5i. And x is equal to negative 2 plus 5i. That means this is going to be x plus 2 plus 5i. And this other one's going to be x plus 2 minus 5i. I'm going to go ahead and start foiling. So it's going to become x squared plus 2x minus 5ix plus 2x plus 4 minus 10i plus 5ix plus 10i minus 25i squared. We have the 5ax and the negative 5ax cancel. The 10i and the negative 10i cancel. And we are left with a little bit less terms. I'm going to go ahead and write x squared plus 4x. And then we have plus 4. This is going to become positive 25 because the I squared is negative 1. Negative 1 times negative 25 gives us positive 25. So I'm going to go ahead and write plus 25. This is x squared plus 4x plus 29. Now we know that 0 is going to work out, so I can go ahead and do long division. So I'm left with x cubed plus 11x squared plus 57x plus 203. And that's going to be divided by x squared plus 4x plus 29. So I'm going to start by x. That's going to be x cubed plus 4x squared plus 29x. Again, remember, we're subtracting, so this is going to become minus, this is going to become minus, and this one's going to become minus. The x's cancel, and I'm left with 7x squared plus 28x, and then plus 203. I want to make sure that the x's cancel, so I'm going to do plus 7. So it's going to become 7x squared plus 28x plus 203. Now remember, we're going to subtract, and it's subtracting the whole equation, so it's going to become negative, it's going to become negative, and this one's going to become negative. So the 7's cancel, the 28x cancels, and the 203 cancels. So we're left with no remainder, and we have x plus 7. Now they want us to find the zeros just like we did in the other one. So we have x plus 7 is going to equal to 0. We subtract it, so we get x is equal to negative 7. And then we have the original x is equal negative 2 minus 5i. And the third one, which is x is equal to negative 2 plus 5i. So this would be your solution. Actually, before I forget, I wrote this one wrong. I just noticed. Is x is equal to 5. X is equal to 3 plus 2i. And x is equal to 3 minus 2i. I forgot to factor this one, so just keep that in mind. Your solution is x is equal to a number. This is for the previous problem. This one I did do it correctly. The homework is already on WebAssign.